The next talk is about the Cosmo-Seismic Task, which has a leader and co-leader. The leader, Noemi Zabari, is not with us, but we have co-leader David Álvarez Castillo.
Just very quickly, I'm just gonna flash out a few of the things that I've been doing in this when it comes to cosmoseismic correlations. From my side, I have to confess that most of the hard work has been done by the summer students. So during the last 3 years, I've been working during the summer like intensively in this topic. Okay, so so basically I will show something, a few of the things that we've been doing with the students, and also I will try to summarize what Noemi also presented in the morning from the side of Astrotech. So we are looking for signatures as possible precursors of earthquakes from cosmic rays. And for that, I've been using like 2 techniques. So from another field I've been working with, that is compact stars related to astrophysics, but also these techniques also apply to cosmology and so on, are Bayesian analysis. And the Bayesian analysis is basically using the so-called Bayes theorem that everybody who is in the science field learns at some point in the statistics class. So basically, the Bayesian analysis allows for studying models or for providing probabilities of some event to happen. And the Bayesian theorem is basically here. So basically, we need to have some prior, that is some probability that we have to define, or where we expect of something to happen. Then we have some likelihood, another probability distribution, that is the likelihood that has to do with the probability of some data to be true given some theory. And and this is usually divided by the so-called evidence, that is also some other probability. And once this formula is applied, then we can come with posterior probabilities, and these posterior probabilities can be used to compute expected values, just like in standard statistics. So this is how it is usually used. And in the case of this can be used also for either for parameter estimations of some models, but it also can be used for inference. As an application for the cosmoseismic analysis, we consider the example of the change point. So we consider, if you think of a signal that is described by a standard deviation and also a mean value, and at some point this signal changes to another standard deviation and mean value. So the idea is to figure out where this happens. So this is the so-called change point, and this is a textbook example. So out of this data, by using the Bayesian analysis, one can find the probability distribution to find the peak of this change point, and this can be, I can refer to some textbooks where this is done. So basically, this is just an example, and this is just a technique. So we decided to look into that for the earthquakes and cosmic rays data. So we tried to find a change point, and out of the work of Alexandre Skorenok and Ofir Ruimi, that is actually probably present here, and they found some change points in both the earthquake rate and the cosmic data from Auger. However, the change points do not coincide, so we are still trying to figure out what's going on. Next year, also Clementine Bartosz and Ofir, who has been involved. I would like to highlight that Ofir has been very much active within the collaboration. So they also studied change points. So at the moment there are just some hypotheses, but this is still like work in progress. We need to understand if what do these change point mean and how can they be associated between the two sets of data. We're looking at both cosmic rays and seismological signals. Also, the students, together with the students, we have also looked at the correlation between the cosmic rays and the seismic data, just like as we have discussed in the meeting out of this paper of the last year. And we tried, I mean, the students have brought with some ideas that the fluctuations of the flow of the outer core could be the reason for this correlation. This has not been proved. However, the hypothesis, and this hypothesis has to be tested, is that the outer core produces the magnetic field of the Earth due to this, that because of the outer core that produces the magnetic field of the Earth, and because it moves, there are movements, and these disturbances out of these motions can affect the magnetosphere, because the basic idea model is that the Earth is the core of the Earth behaves like a dynamo, and this can possibly have an impact on the rate of detection of cosmic rays, as they can change their trajectory. And we're of course thinking of charged particles that fill the magnetosphere of the Earth. So they found this model here, where the authors propose this turbulent geodynamo scenario, and there are simulations. So this is still it's very interesting and promising. I think one can still look further into modeling and maybe taking their simulations or trying to do certain or other kind of studies. And interestingly, last year, Barbara Farkas and Alexandros Milonas, also working in the summer students particle physics program here, they look at the correlation. They use the same methods that was used in the paper, last year's paper, but they, instead of looking at the global behavior of this of the data, they start to look at the stations in localized. So they look into Middle America, and they found some sort of different types of correlations using exactly the same method. They also look into Middle East using the stations at different locations, and around Japan. So these were like three representative areas where the earthquakes tend to happen. They used 11 cosmic ray detectors. They found something like around 5 sigma correlation in Japan and the one in Finland. And there's another idea, at least discussed, that could be interesting to also to look to data, if they exist or not, of this phenomenon, not only on the Earth, but also in other planets. This is, of course, very, very ambitious, but still, if it happens here, why not in other celestial bodies? And of course, the machine learning algorithms is also an interesting tool. And this is exactly what Noemi discussed this morning. So I took these slides from her presentation. This work is being carried by Kamil Zielinski and the group of Astrotech. And they asked the questions of how many earthquakes can we detect in advance, and what is the false alarm ratio at the specific detected earthquakes level. So they develop some method with the so-called earthquake focus metric under these assumptions, that if the false positives and the true positives have to be counted in a 14 days period. A false positive is recorded if any false positive alert occurred within this 14 days period, and a true positive is recorded if any alarm occurred within this period preceding an earthquake. And with this, they have made the analysis, and they have derived this baseline false alarm, and the models detected. So they computed a statistical significance test after performing 300,000 experiments with a different seed, and the predictions were uniformly distributed, random numbers between 0 and 1. None of these experiments could exceed the AP performance of the model, and that indicates a strong significance of 6 sigma or more. And they conclude that the machine learning approach that they have been applying tends to confirm the existence of the cosmic seismic correlation that we presented in the paper last year. And there's hope that they could translate into significant real world effects. It seems that we can forecast at least a few % of massive earthquakes within a decent false alarm rate below 13%. Well, they stress that it's important to remember that earthquakes are currently almost entirely unpredictable. At least this is a paradigm. This result could be a starting point for more significant findings with the potential to save, of course, thousands of lives. Thank you.
Thank you, David. Okay, we don't need to discuss because maybe this last part was basically introduced also by Noemi. We are pleased to see that there is more activity. Also, students are active. So again, this task is open for more contributors, and we are happy that you took the lead with Noemi. Or
Thank you.
maybe there are questions. I don't know. No, I don't see.